Yeah. All right. What about that? You can show me the new tool that you made for the
This
test
tool.
automation.
Sure. I made this automatic test case simplification tool
Mm-hmm.
called well, it's simplified test case.py, and I've been pretty happy with it. So test case simplification, I guess. So test case simplification, right, is when you have like some weird error, but you know it's coming from this file, but you don't know exactly where from this file,
Mm-hmm.
or not necessarily a file, but in this tool only works with a file, but it could
Mm-hmm.
be, for example, why like this entire code base like
Mm-hmm.
it's generating some very weird error. The error is not telling me where it is coming from.
Mm-hmm.
I just know that this very weird error. So what you
Mm-hmm.
do is you try to simplify this test case to the bare minimum that still generates this very weird error,
Mm-hmm.
and then now you have less stuff to look at.
Mm-hmm.
And I actually, yeah, if I made a video, right, on debug school. It's on YouTube, debug. Just if anybody is interested, I made a video about that. It's you go to debugschool.com, number 5, test case simplification. I have a more in-depth explanation of what that is.
Mm-hmm.
Uh, and this is a technique I use a lot whenever I really want to solve a bug,
Mm-hmm.
and the error message is not giving me any help. I use this a lot. Um, and then a couple of days ago, I decided to make a tool that does this automatically for me. So
Mm-hmm.
because usually this is a very tedious process.
Right.
It usually is like, oh God, I have like a very large file. I'm gonna selectively delete chunks of it. Um,
Mm-hmm.
Maybe I'll so maybe like to show an example of this. Let's say I
Mm-hmm.
have a file like this.
Wait,
I'm
are you
gonna,
sharing your screen or
oh, let me share my screen.
sure?
Okay, can you see my screen?
Okay. Yes.
Okay, so yeah, so let's say I have a file like this. Uh, I'm calling this file test2.py,
Okay.
and just to introduce an error here, maybe I forgot to close this parenthesis.
Right.
Um, now for the case of Python, we actually do get a kind of a the error message is good enough in
Mm-hmm.
Python that you can normally figure it out. But let's say
Okay.
let's pretend it's a more cryptic one. So let's say
Okay.
you couldn't figure it out. So if but I was using this with more cryptic error messages, and it worked very well so far. I'm pretty happy with it. So
Mm-hmm.
it gives us this error message. It says line 170. It's pointing to the next line,
Mm-hmm.
to the one where I made a mistake.
Right.
So to some people that might be very cryptic, and they're like, "What? I'm looking at this log file. I don't see anything wrong." So they have no
Mm-hmm.
idea what's going on.
Right.
Maybe they didn't think to look at the previous line for the
Right.
mistake.
Mm-hmm.
So what you could do if you had this tool is you write a execute function. I have a couple of them here. I haven't
Mm-hmm.
extracted this out to be a reusable tool just yet because
Okay.
I just made it 2 days ago. But
Uh-huh.
but the idea is you write an execute function, which if you ran the function, it returns true if and only if that cryptic error is happening, and
Okay.
it returns false if that cryptic error is not happening.
Okay.
And so the way I'm gonna do that is by running this command.
Mm-hmm.
I think this does that. So this runs Python 3 and then this file. I'm typing
Okay.
Python, but it's same as Python 3 in this case.
Okay.
So,
Mhm.
so I'm getting Python to do the same thing I'm doing on my command line, and then I'm actually going to decode these. In this case, it should be the error. I'm gonna assume, first of all, the cryptic error presumes that the return code is 1. Return code is 1 means the program has failed. It's return whether. So I'm gonna say if it's 0, if the program went through with no error, that's actually a false. That's an absence of the cryptic error.
Mm-hmm.
Okay. And then I'm gonna say, I'm gonna decode the standard error, that error message that get printed out. I'm gonna grab it. I'm gonna split it into the error lines. And for now, I'll print it out to know what to match. And then I'm gonna test out my execute3 function first before I use this tool on it.
Mm-hmm.
Okay, so these are my error lines.
Right.
So I'm saying, hey, this is my cryptic error, and I want to match this cryptic error. I want to say, if this is true about my error message, then yes, I'm seeing this cryptic error.
Okay.
So what I'm gonna do is say, hey, if how about if this line says syntax error, invalid syntax, and this would be -2, index -2 for Python, because Python can have negative index
Okay.
syntax. So error lines -2 is the second from the back.
All right.
If the second from the back is syntax error, invalid syntax, and then this is the third one, the fourth from the back is log file.flush.
Okay. Yeah, like negative syntax. I mean negative index. That's nice.
So I'm gonna say match 1 is that, match 2. If both of these conditions match, then I'm gonna say that is the signature for my cryptic error.
Okay.
So I'm gonna say match 1 and match 2. If both of these lines match, then the cryptic error exists. So let's see, and I'm gonna print the result of this function. It says true, and if I remove this error, or if it's like a different, if I remove the error, it says false. If it's a different error, then it's false. But only if I made this error, then it's true. Okay.
Okay.
So that's what how you're supposed to implement your execute function. Now, once you have this execute function, you plug it into this simplify test case function. It's execute3, and then you tell it the file that is the input to this, that goes into this test case, which is this test2.py file, and then you start running it.
Okay.
So let's run it.
What does it do? Like a binary search?
Yeah. So what? Oh, it just completed. So after it completed, it has reduced the file down to these lines. And then now you only look at these lines. You can probably find it at this point, right? Okay.
So what does this do? What does the simplify test case message do?
What is the algorithm? So the algorithm is implemented in this function, which is not that long. It's maybe 50 lines or so. Yeah, maybe 50 lines or so. The algorithm is basically and also it backed it up into an original. So it backed it up into the file name .original. So this is the original file. And also, while it's going, if it the intermediate steps. Well, let me explain the algorithm first. So basically, it tries to do the binary search thing that which is, hey, cut out half of the file, like right down the middle, like just delete the bottom half of the file and then redo the test, right? And then if you do that and redo the test and you get the exact same cryptic error, then the bottom half is not needed to generate the cryptic errors, and then you keep going. You subdivide it again. I wanted to make this. One problem is sometimes you cut it off at the halfway point, and then you end up with invalid syntax.
Right.
Or you break the existing syntax, right? So what you do in that case is, if you break the existing syntax, like you cause a syntax error because of your modification, the syntax error should usually be a different syntax error. Like the signature of your error should be different, so that your execute function generates a false. Which is why I made this very specific, this matcher very specific, so that if you cause a syntax error that's not this one, then this execute function actually returns false, right?
Right.
And therefore, if I cut it off at the halfway point, like I did it here, and it's going to be a syntax error because, well, you can't have an empty function body like this in Python. That will give you a different syntax error that doesn't match this one. And then in that case, what it does is it will undo that operation. It'll undo it and it'll try again. And then how do I try again? I subdivide it even further. I divide it into 4 pieces next. And then I try piece by piece. I try each of the 4 pieces. Try deleting each of the 4 pieces. I subdivide it. So basically, initially, I have the divisor set at 2. I divide it into 2 halves and delete. And I try deleting first the top half and then try deleting the bottom half, and see if it gives the same error. If it gives it the same error, I'm keeping that, right? But if it's a different error or different output or no error, then I undo that, and then I double the divisor to 4, and then I try removing each of the 4 chunks. If that still doesn't work, I doubled it again into 8, and try removing each of the 8 chunks. And then if it worked at any point, then we're keeping that. So yeah, you can see, problem persists. We're keeping that change. But if it's if the output changed, we're undoing that operation. Does that make sense? That's all this is doing. And the nice thing about this, I think, is that if you were a person doing this intelligently, you would definitely be looking at the syntax to prevent from breaking the syntax, right? You would be like, hey, this is a chunk, I'm gonna delete this chunk, right? That's faster, and that's a more efficient way to do it if you understand the syntax of the program. And I could have done that. I could have used a Python parser to parse the structure and then just remove like certain syntax node from the tree. But this scheme, I like it because it can work for any language. It doesn't matter. It's slower, but it'll work for any language. Doesn't have to know what language the input file is in.
So in order to, so the program will return or will complete until you divide it or you remove how many lines, and then the program will have no errors, and then you're like, okay, this is my lines that I identified that causes the problem. Is that how you define how the program will stop?
No. It still has an error. First of all, at this point,
Okay.
it still has an error because the syntax error is still there. It is we forgot to close this parenthesis.
Okay.
So
But if you remove these two lines, then there will be no errors, right?
Oh, it actually, the result is not the smallest possible result that it could be.
Uh-huh.
And I could do something to make it absolutely smallest possible result. It could be, but I thought this was kind of good enough. But basically, the stopping condition is when the divisor, when the number of lines divided by the divisor is less than 1, then the program stops.
Okay.
So the divisor is going like initially you divide it into 2 halves.
Right.
So the divisor was 2, and then the number of lines in one of the halves is like 125 probably.
Right.
And if that didn't work out, it has to undo, and then it doubles the divisor to 4.
Right.
And then it doubles the divisor. If it doesn't work, it doubles the divisor to 8, and so forth. So eventually, if nothing is working, the divisor will be big enough so that the chunk size is 1, maybe, and then it's only removing 1 line.
So basically, when the divisor become really large, and it will remove 1 line at a time and rerun the program each time until.
Or just the remaining program has been sufficiently small that even with a small divisor, you get a line of 1, a chunk size of 1, right? Like this, it has reduced this down to 4 lines at this point. So the divisor only has to be 4 for the chunk size to be 1.
Oh, okay. So okay.
And whenever you keep something, whenever you succeed in reducing the file, you delete this chunk and you still get the same error, right? Whenever you succeed, you reset the divisor back to 2, right?
Oh, okay. So the stopping point is actually like after you remove everything else, and then you have a very small program that still produce the exact same error. And
exactly.
Okay, gotcha.
So exactly. This program produces the exact same error. Yeah, we see this exact same, or not exact same error, but this error as based on our matching code here that we define in our execute 3 function.
Gotcha. Yeah, I think that's really smart. So what would there be a case that this program just not able to find out, just not able to build a small program that's producing the same error? Will that be possible?
I guess I can. Theoretically, it can be possible. Like, I can definitely contrive an example of like if the process of like you can read in the entire file, like and detect if the file is exactly that way, and if it is exactly that way, you spit out this error. You spit out this cryptic error. You can write a program that does that, and then if the program that you're using to test it is doing that, then yeah, any change you cause to it will cause the cryptic error to go away. Right. That's a very contrived example, but
Okay.
in real life, that is usually not the case.
Mm-hmm.
In real life, it's like there's some small thing inside a big file that's causing the
Uh-huh.
problem, or a combination of a number of small things inside the file.
Uh-huh. Gotcha.
Yeah, like you can think of like a maybe more intuitive thing is like, uh, what if you just deleted one line from this file at random
Uh-huh.
and retested it? Does it still have the cryptic error, right?
Mm-hmm.
And if you did that, if feels maybe it's maybe pretty likely that you can remove a random line and still have the same error, right?
Mm-hmm.
Uh, yeah, and you could do that algorithm, but that would take a lot longer because there are a lot of lines in this file, right?
Yeah, I guess as a human, if I do this, I will more be like, instead of just deleting stuff, I will like say just remove a functionality that I know. Say like this chunk represent this
Yeah,
functionality, so I will
yeah,
represent this block, this block, this block, and then I
yep,
will test again. But
yep.
I can't test as fast as this program.
Yeah, exactly. This is more brute force and it's dumber than you, but it can do calculations faster than you can.
Yeah, yeah, I think
Uh,
that's very cool. Yeah,
yeah,
I definitely see a great value of this, especially for the program that it's like a thing that will produce either an error or something else. Because sometimes the bug is not like it's producing an error. The bug is the behavior is not what I think it would be. Like if I
mhm,
do a calculation, the calculation is the number that's not, I don't expect something
yeah.
like that.
As long as you can write a matcher that detects that weirdness, then
Mm-hmm.
this concept can work.
Yeah.
Um, yeah, and for like web applications, which most of us work with, um, this is still possible, but you might need to do something like spin up like a like a headless browser or something to
Uh
test
huh.
your web page, like Chrome headless, or
Mm-hmm.
Puppeteer. Puppeteer is a good tool for this. Um,
Mm-hmm.
spin up a headless browser, load your web page in there, and that is more work, and it can put. And if you're using TypeScript or something like that, you have to tell TypeScript to recompile the thing,
Mm-hmm.
and wiring it into your existing tool chain might be trouble, but it's definitely doable, even for that.
Yeah, the thing is you need to write out your test case using like Puppeteer, right? You need to say, hey, this is the behavior I want
Yep.
to
Yep.
see. I want to see two buttons on the screen, but why there's only one?
Yeah. 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 That part of it, still